Welcome everybody to SQL Friday. This is SQL Friday number 52, but in fact it's the 50th SQL Friday because we have had two cancelled SQL Fridays. So I had kind of a small celebration inside myself 2 weeks ago. So let's have another one. This is, as I said, number 52, and we have two more for the summer. So the last for this season is going to be on midsummer, which is always interesting because it's a day off for many countries, but that's how it is. So, but today our star and guest is Torsten Strauss. And when Torsten sent in his abstract to SQL Friday to the call for speakers, I didn't know that when he's going to make his presentation, I actually work with him on a daily basis. But it's really nice to have you here, Torsten, although we nowadays talk a bit more often than we did when you sent in the abstract. But I'm really looking forward to this, what I think will be kind of a deep dive into parallelism in Microsoft SQL Server.
Mm-hmm.
So, Torsten, the stage is yours. Just take over the screen share when you are ready.
I'm ready. 1 second. Just want to take over the screen. Let me hijack the screen.
Yes.
And the good thing is that for some reasons, it seems that my PC is doing something in the background.
So I see a dark screen. It's pitch black.
Yeah, that's nice. That's nice. This is what I really like. Yeah, this is whenever you present, Microsoft is doing something in the background and nothing is working anymore. So believe me, I cannot do anything at the moment. 1 second, I need to give the PC a moment, maybe, and hopefully it come back.
Yes. What I could do maybe is if I share the screen again, because then now I see it.
Well, yeah, great. It's coming back. That's fantastic. So
awesome.
Yeah, it's really unbelievable. You can see my memory impact because of Desktop Manager. Windows Desktop Window Manager. I have no clue what is going on here, but let's hope it works. Yeah, you can see my machine is busy even without doing anything. Yeah, so that's great.
Nice.
Nevertheless, let's give it a try. And yeah, so let's see whether the technical pre-requirements will work over the session. So that's me. I'm Torsten Strauss, as already mentioned by Magnus. Thanks for the opportunity to speak another time at SQL Friday about parallelism, as already mentioned. So, and I guess parallelism is definitely something which is not a very easy topic. And there are a lot of surprises, I would say, because I started to learn about parallelism maybe a year ago. So really doing a deep dive. And for me, some of the findings were really surprising because it is the opposite what you normally read in a documentation from maybe Microsoft or other people. Yeah. So therefore, I cannot promise, and I'm sure that we will not finish because this is a session which has more than 3 or 4 hours of examples. But we can start for sure, and let's see how far we can go over the next 60 minutes. Okay, so what is parallelism? You can see I wrote down a few things here. So SQL Server can execute queries using multiple CPUs or cores at the same time. That is mainly the description about parallelism. So the idea is that whenever your query is running and the SQL Server Query Optimizer estimated the costs in advance and compare the estimated cost with the cost threshold for parallelism, which you can set on an instance level. Yeah? So whenever it is more expensive, then SQL Server considers to think about a parallel plan. So for 1 second, I'm losing the screen here. Okay, so Magnus, can you see Management Studio?
Yes.
Okay,
I see it
so
now.
okay, for some reasons, I got something like a black screen or whatever, which is better than a blue screen. Okay, so the problem about parallelism is that parallelism has a lot of disadvantages, and for sure sometimes advantages, especially when it comes to the query elapsed time. So some of the queries are running faster when you allow SQL Server to execute the query in parallel. This is more or less true for, I would say, data warehouses where you deal with column store indexes. But believe me, most, or I do not want to say most, I do not even want to judge, but there are several OLTP queries which are running much faster when you disallow SQL Server to run the query in parallel. Yeah, so this is something which was a little bit surprising for me, because I was always thinking that whenever the cost threshold for parallelism is less than the estimated subquery cost of a query, then SQL Server has good reasons to implement parallelism. But this is just the estimated cost. There's nothing about, and this is something you always have to consider when you look into an execution plan. The execution plan does not have anything about actual costs. It only has estimated costs. That means SQL Server, again, must create an execution plan. And the execution plan is based on cardinality estimation. And the cardinality estimation is nothing else than the number of rows SQL Server thinks the engine has to process to execute the query. But if for some reasons the statistics are stale or the statistics overall are not precise, then either SQL Server underestimates or overestimates the number of rows, which will lead or which can lead to a non-optimal plan. And this is one impact. The other impact for sure is that the estimated subtree costs are not precise. These are not the actual subtree costs, as we will see. And this can lead to the problem or to a situation where SQL Server considers a parallel plan. But when you execute the same query with a different parameter set or whatever, think about parameter sniffing, the parallel plan is far away from from the best plan comparing to the serial alternative. So this is something which you always have to keep in mind. Parallelism is just based on the estimated subtree costs, nothing else. As we will see, there are some operators, like the top operator, for example, they, from an algorithm perspective, they cannot run in parallel because of the algorithm, right? And this is also something you have to keep in mind, because maybe you wonder why the query is not running in parallel. Even the costs, the estimated subtree costs, are much higher than the cost threshold for parallelism. And the reason for this is that you have very likely, an operator in your execution plan which cannot run in parallel. So that means the query never ever have a chance to run in parallel. So that's it. Okay, let's try to understand what SQL Server, which kind of pre-requirements SQL Server have to, which technical requirements SQL Server have to have. So the SQL Server must run on a multiprocessor, multi-core, or hyper-threaded machine. I think this is for most of the SQL Server you are working with. This is the case. Processor affinity configuration must allow SQL Server to use at least 2 processors. So, and by the way, when we talk about the processor affinity mask, so this is something which you will see here in processors. So, and you can, if you like to, you can configure the process affinity mask here for the I/O or for overall, which is sometimes a good idea when you have more than just one service running on the same on-premise machine or the same host. But you have to be very, very careful. I will skip this part, but there is one trace flag which you have to set, because otherwise you disallow SQL Server to move one scheduler to to another core, which means when one core is really, really busy and you do not set the trace flag, but you set the processor affinity mask, the scheduler, which is considered a scheduler like a logical core, which is running on a specific core, right? And when you do not set the trace flag, this scheduler is bound to a specific core. And when this core is very, very busy, you already run in a blocking situation. So that is the reason why Microsoft has one internal trace flag, which makes sense to set whenever you set your processor affinity mask, because otherwise SQL Server cannot move to another idle core in order to balance the workload on your CPU. So this is something I just want to admit. I can demonstrate, but this will take at least half an hour. And that is the reason why I decided to skip this one. So the next one is the maximum degree of parallelism must be set to 0 or something which is more than 1. For sure, otherwise SQL Server cannot use other cores by instance configuration. So the maximum degree of parallelism for the resource governor must also allow the use of parallel plans. And this is something which I really like, because the resource governor, which is an enterprise feature, by the way, gives you the opportunity to set the maximum degree of parallelism for a specific, let's call it resource pool. So that means some of the connections you are using have the possibility to run queries in parallel, and some of your connections cannot use parallel or more than one core for one specific query. So this can be very, very helpful. Oh, there's a big echo. This can be very, very helpful in order to balance the workload on a SQL Server enterprise machine. So the last one is the estimated cost to run a serial plan for a query is higher than the value set in the cost threshold for parallelism. This is what I already mentioned. So just to give you an impression about the DMVs which we can use, there's one DMV. This is this DMO is this info, which have a bunch of more columns, but the 3 columns you can see here, or the 2 columns, which is CPU count and the hyperthread ratio, will give you the information whether your SQL Server can run queries in parallel. So that means I have currently 1 physical CPU. I have 8 logical cores within the physical CPU because my machine is hyper-threaded. This is something which you have to check whenever you have to do some performance tuning on a server you do not know. So there are a lot of information related with these or to this DMV. Processor affinity mask, as already mentioned, I will skip. Let's go to the, I set some bookmarks here, but for some reasons, it is not working. Okay, then I need to scroll. Sorry for this. This is the processor affinity mask, something I will skip. But we can start with the maximum degree of parallelism. So in order to set the maximum degree of parallelism, you can either go to the GUI or you can use the SP configure, cost threshold for parallelism, which is by default 5. And most people ask the question, why the hell Microsoft is not changing the value over time? Because if I remember correctly, this is a value which was set in, I don't know, maybe 1990 or whatever. So very, very old. And if I remember correctly, the interpretation was that when a query runs longer than 5 seconds, then it is worth to think about parallelism. This is because the CPU power increases over time. This is for sure a value which is not, how can I put it? Which is not the best one anymore. So, but the problem is Microsoft cannot set another value here, or it can, but it doesn't make any sense, because the cost threshold for parallelism is really dependent on your workload, dependent on your architecture, on your setup, everything like this. So even if Microsoft now changed to 50, this can be good, but it can also be bad. So there is no best guess. And that is the reason why Microsoft decided to stick with 5. Yeah. Again, but when you set up your SQL Server, this is one of the first settings you should change, because otherwise it is very likely that most of your, no, not most, but yeah, the majority of your queries are already running in parallel. Yeah. So, and this is something you want to avoid. So when I execute this query, for example, which is great. I forgot to, 1 second. I just need to create a table. It only takes a few seconds here. This is normally something I will do in advance. Okay, this is just a test table with a few records. And again, I will execute this query. So I just want to make sure that, 1 second. So this is maximum degree of parallelism. I set the maximum degree of parallelism. Yeah, we are back. So just want to check that everything is working. Yeah, so the value is in use, which is 0 for maximum degree of parallelism. That means SQL Server can run queries in parallel. So when I execute this query here, and I will show the execution plan, so we can see this query. Why it is not running in parallel? 1 second. That's great. Just need to check whether the settings are correct. 5, yeah, should work, but okay. I think the problem is that sometimes it is not predictable. It is very close to 5. Let me do the following. I will go to advanced and set cost threshold for parallelism to 3, because the subtree costs are estimated as 4.7, if I remember correctly. But let's give it another try. So now it is running in parallel, as you can see. So this is because the cost threshold for parallelism, you can see it here, is or the other way around. The estimated number, the estimated subtree cost of 1.6 is now smaller than the cost threshold for parallelism, which I set to 3. But when I run the same query with a hint, MAXDOP 1, I can see the cost, which is related to the serial plan. And the serial plan, as you can see, is 4.6. So that means this is the threshold. The threshold is 3 on my machine currently. That means whenever the costs are greater, the estimated subtree costs are greater than your cost threshold for parallelism set on an instance level, SQL Server considers running the query in parallel. Yeah. So again, some of the queries will never ever run in parallel because of the operators, the physical operators here, SQL Server use in the execution plan. But in general, whenever the estimated subtree costs are greater than your cost threshold for parallelism, which you set on an instance level, SQL Server try to run the query in parallel to save some costs. Yeah, that's it. Okay, I will skip this one. Just want to make sure that I reset everything. MAXDOP is set to O, and because I also changed, I can do it here. Just want to reset everything that it is working. So resource governor, as already mentioned, I have to skip this example because otherwise it takes too long. But again, this is a very, very nice way to limit the maximum degree of parallelism for specific connections. Yeah? So think about maintenance, think about, I would say, user queries with a high priority. This is something which you can handle with a resource governor. So let me skip this. Yeah, cost threshold for parallelism. I guess I already explained what kind of impact it has. So I can skip this as well. Yes, there's one. Sometimes you're wondering why a query is not running in parallel. And you want to compare a serial plan or the serial plan with the parallel alternative. And for sure, you can change the maximum degree of parallelism. You can change the cost threshold for parallelism in order to force SQL Server to run a specific query in parallel. But even then, some of the queries are not running in parallel. But there is a hint. There are two hints. One hint, which is the query trace on 8649. And I think since SQL Server 2016, if I remember correctly, there's another hint, a query hint, which is enabled parallel plan preference, which exactly behaves the same, where you can force SQL Server to run the query in parallel. So when we execute this query without any hint, we can see that the execution plan, this is a serial execution plan, so no parallelism. Now and the costs are, you can see it 1.8, so which is less than the cost threshold for parallelism. That is the reason why SQL Server will not run the query in parallel. So now I can force SQL Server to run the query in parallel to see the savings from a cost perspective. So let me execute this one. And you can see this is exactly the same query as before, but I force SQL Server to run the query in parallel. So the estimated subquery costs are now down to 1.3, which is, if I remember correctly, something about 0.3 of cost saving. But we will see in a minute that the elapsed time and the CPU time for this query is even higher than before. That means there is no advantage of using a parallel execution of the same query here, right? But again, sometimes you want to see how the query or the execution plan looks like when you force SQL Server to run the query in parallel. And again, you can do the same with the hint, enable parallel plan preference, which is another parallel execution plan. Perfect. Processor affinity, I already mentioned that there is one important trace flag, and I think it was 8002 or 8001. Let me try to figure it out, because this is something which you have to set. Let me go down. Again, this is will already take half an hour or whatever just to present this one, but I just want to see the trace flag. It is 8002. So whenever you set your processor affinity mask on your machine, please Google for trace flag 8002, which gives you a clear understanding about the benefit of setting the trace flag globally. So let me skip this one because I only have half an hour less. The next thing from a resource or from a hardware architecture you must understand is the Numa Node. So nowadays we have CPU's architecture, which are called Numa Nodes. Before we had something which was called Uma Node. So the Numa Node is something which is very important to understand. So consider the following. We have two CPUs, two physical CPUs, and each of the physical CPU have 8 logical cores. So that means in the end, we have 16 logical cores, two physical CPUs. So which is, I would say, a very common configuration for a SQL Server. Most of the SQL Server I have seen so far are running at least on 2 Numa nodes. So, but we have a problem. The problem is the following. When you understand how Numa works, then you realize that whenever you have to exchange data between one physical core, one Numa node, and another physical core and another Numa node, the exchange of data happens by the bus. And the bus is something which is slow, much slower than exchanging data within the same Numa node, between the logical cores which are related to the same Numa node, because this exchange is done by the cache. And the cache exchanging data by the cache is much, much faster than using the bus. When you now consider the following. You execute a query in parallel, and you allow SQL Server to use all cores to run the query or to execute the query in parallel. Then you already understand the performance implication. SQL Server now must exchange data between the physical cores or the Numa nodes, which means SQL Server will exchange the data by using the bus. This already has a performance impact, which completely slows down your query. That is the reason why SQL Server or Microsoft recommends to set the maximum degree of parallelism to the number of logical cores within one Numa. So let me open the latest recommendation from Microsoft. So Parallelism MAXDOP. This is something which I took from the official Microsoft documentation. It's the latest one for SQL Server 2016 plus and for older versions. And you can see that the recommendation is the same. There's just one condition where the guidance is different. So when we have SQL Server older than 2016 and you have more than 8 logical processors per Numa node, then the guidance is to keep the maximum degree of parallelism at 8. So when we compare this with the newer version of SQL Server, so 2016, 17, 19, and you have more than 16 logical processors per Numa, which is the same, I would say this condition is the same as this condition. So that means keep the maximum degree of parallelism at half of the number of logical processors per Numa with the maximum of 16. So you can see the maximum is 8 for older versions. Now for newer versions, SQL Server can even use more logical cores to execute queries in parallel. The reason for this is that SQL Server for sure did some internal, I would say, changes here in order to give SQL Server the possibility to benefit from more physical or logical cores. But the reason that SQL Server or Microsoft decided to implement this, I would say, the change here is that SQL Server have to deal with more and more records. And more records means that the estimated subtree costs are increasing. And the more data we have to handle, the more likely it is that a query will benefit from parallelism, right? But this is not a typical OLTP scenario. In an OLTP scenario, you are dealing with a smaller set of records. In a data warehouse, and you can imagine that data warehouses are growing over time, SQL Server now can benefit from double of the CPUs to run queries in parallel and to save time, so to make the user experience better. So this is a big change. But again, this is only important for data warehousing, not for OLTP scenarios. Let me go back. So I'm currently just on my personal laptop. That is the reason why I only have one physical core, 8 logical cores within one Numa, right? But there is one DMV, which is called this DMOS nodes, which give you an idea about the number of Numa nodes you have on your machine. And you can also set up logical Numa nodes. And this is something SQL Server, I think since 2017 or since 2019, is doing automatically when SQL Server starts up and detects that the number of cores within a Numa is greater than a specific threshold. But in former versions and even with a new version, you can set up logical Numa nodes. The reason why people was thinking about implementing logical Numa nodes was that there was one hint from Microsoft, I guess, that it can run faster because of the so-called lazy writer process. So the lazy writer process takes care about the buffer cache. So the buffer cache is nothing else than the data pages SQL Server saves in memory in order to avoid physical I/O. Instead, provide logical I/Os. The reason for the lazy writer is the following. Now consider your data buffer pool is 100% full. And now you have to read data from your MDF file because the pages you request are not available in the buffer yet. That means at that moment, SQL Server has to release space in the buffer pool because, again, it is full. That means SQL Server has to flush a specific number of pages in order to get some space. And this is something you want to avoid when a user executes a query, because this is an overhead. It takes time. It is nothing else than a physical operation, because the pages SQL Server have to flush out are most likely dirty pages. And that is the reason why it is a physical write operation. And the physical write operation is something which is still horrible slow. So the lazy writer in the background will evaluate the available space within the buffer pool from time to time. So it is a background process. And I think there was something mentioned in Microsoft documentation. It is not available anymore because the statement was wrong. That when you have more than one logical Numa node, you have, let's consider you have two logical Numa nodes, then you have two lazy writer processes. That means a lazy writer process can run in parallel, right, in order to handle the number of pages within the buffer pool to make sure that you have some space available whenever you need a physical read operation. This is not true. The lazy writer is only there once, even if you have 2, 3, 4, or even more Numa nodes. So there is no reason to set up a logical Numa node. Do not set up your own logical Numa node because of the lazy writer. It will not work. So nevertheless, when we look into this DMOS nodes, you can see that we have two nodes, but I already mentioned that I have only one physical core with one logical Numa node. You can see that we always have one node 0 and we always have one node 64. So even if I have more Numa nodes, I will end up with 3 entries here. That means I have always one additional Numa node, which is the DAC connection. So the dedicated administration connection, which gives you the possibility to access your SQL Server whenever SQL Server is not accessible anymore. This is the so-called DAC connection. And therefore, SQL Server have to create one internal logical Numa node to handle your connection, to handle your requests, right? That is the reason why we have always one additional internal logical Numa node. So there is another DMV, which is DMOS memory nodes. And here you can see additional information about the Numa nodes. So you can see the virtual address space reserved kilobytes and so forth, which already gives you an indication about how many or which kind of memory is currently allocated to the logical Numa node. And this is important whenever you see, I would say, a disbalance, or when the memory is not balanced between the Numa nodes. This can already give you an idea that for some reasons the internal CPU, I do not want to say architecture, but the processes are not, or for some reasons, are not working properly, right? So there is another DMV which is called this DMOS memory clerks, and that is interesting because what you can see here is when we do something like this, we have one column which is called memory node ID, which is in my case always 0 because I have only one Numa node. But when you run the same DMV on a machine which have more than one Numa node, you will see that the number of 349 is doubled -1, because -1 is related to the lazy writer. That means for every logical core, you have a specific memory node. Consider this as a cache. And one cache is a data buffer pool. And again, that means when you now exchange data from one Numa node with another Numa node, because you didn't set your maximum degree of parallelism properly, then you are already in trouble because you have to exchange data by the bus and not by the internal cache, right? So that is something you always have to consider when you set up your SQL Server. Yeah, I will go down. Yeah, okay, this example just shows that all the pages will go to one Numa node, and there's another example to force that the data pages are balanced between the Numa nodes, but this only makes sense when I have a machine which have more than one logical Numa node, which is not the case. Yeah, I do not have VM in front of me currently. Just want to reset everything, just to make sure it is working. So I already talked about the bus and the cache. Yeah, so the exchanging data by either the bus or by the internal cache between the logical cores. So there's one tool which you can download from Microsoft for free, which is called Core Info. And when you run Core Info on your machine, and this is what I really highly recommend, you will get information like this. So there's an approximate core across Numa node access costs. So you can see it in line 1957. So what you can see is that because of the internal cache, there is no latency between the same Numa node. This is what I already told you. But there is a latency of 20, respectively 30% when you exchange data between the Numa node 0 and 1. And this is something you have to consider. This is something you already lose. This is 20 up to 30% on this VM here. And I have seen even 50% of latency. So that means you are losing 50% of your performance from a CPU perspective when you allow SQL Server to exchange data between your Numa nodes. And that is a reason, again, why you always have to set your maximum degree of parallelism to the number of logical cores within one Numa, at maximum 16 in SQL Server versions since 2016. Great. Okay. Now, I did the following. I think we have the idea about the architecture, the CPU architecture, in most of the settings which are related to parallelism. And there is one query. You can see the query here. When I execute the query, we should see something like an execution plan. And let me do the following, because otherwise it takes too long. I just want to execute or display the estimated execution plan. So this one is running currently in a serial way. But you can force SQL Server to run the same query in parallel with a maximum number of 1, 2, 3, 4, 5, 6, 7, and 8. So this is the way I did it. So I execute the query with the right settings so that the query can parallelize. And I measured the time for the elapsed time, the time for the CPU time, and for sure the wait time. Because the elapsed time, so the overall execution time, is nothing else than CPU time plus wait time. Yeah. So, and this is a report. These are the numbers. And this is very, very interesting to see how it works. So on the left-hand side, you can see on the x-axis, the degree of parallelism. It starts with 1. That means it is a serial plan. So, and everything else which comes next is a parallel plan. And what you can see is, and this is a typical OLTP query, it is not a data warehouse query, right? So it starts with 1, and you can see that the elapsed time, the overall elapsed time, and for sure the CPU time, and therefore also the wait time, is neglectable. It is really, really, really fast. But the more cores we are using, see how it works, the longer it takes to execute the same query. And now we need to consider why it takes longer to execute a query like this when we add more and more cores to the query. So the reason that SQL Server or that the query takes longer is that you have to wait, because again, the overall elapsed time is nothing else than CPU time plus wait time. So, and because I'm running the query with more than 1 core, the CPU time will increase anyway, right? Because it is now n times the number of cores multiplied with the execution time, because every core is busy. But the overall elapsed time is now increasing because of 2 wait statistics. The first one is CXPacket, and the other one is CX Consumer. I think CX Consumer is there since 2016. And normally, I really want to say normally, you can completely ignore CX Consumer, but you cannot completely ignore CXPacket. So CXPacket is class exchange packet. So in order to understand what CXPacket is, you have to understand how SQL Server executes a query in parallel. So it starts with I don't know, with a table scan or with an index scan or whatever. And the index scan or the table scan is already running in parallel. That means there is a so-called page supplier, which we cannot see in the execution plan, which handles the amount of pages the index scan can handle per logical core. Consider the following. We have an execution plan with a maximum degree of parallelism, which is 8. That means SQL Server allocates 8 cores. So when it now scans the table, it will roughly take 1/8 of pages for each thread. This is not always true, because there's several reasons why the number of pages are not balanced. But nevertheless, consider the following. 1/8 of the number of pages will go to the first, to the second, and so forth core thread. That's perfectly fine. The problem now is CXPacket will start to measure the time it takes just for the parallel plan of your execution plan. So that means you always have a gather stream. That means this is a parallel operator which brings all the 8 threads together in order to pass all the rows to the next operator, which is maybe the select operator. Yeah. And the time it takes from the first parallel operator to the last parallel operator, this is a time which is recorded in the wait type CXPacket. Okay, so there is one coordinator thread, which is thread 0. That means when you run a query with 8 threads, you even have 9 threads, because the coordinator thread have to coordinate all the threads which are running in parallel, because in the end, all the threads have to be collected, yeah, in the gather stream, and have to pass to the next operator in a serial manner. So that means when you have a high CXPacket, this will only tell you that your queries are running in parallel, nothing else, because people are always wondering, when I have a high number of CXPacket in my wait stats, is this something I have to worry about? No, you do not have. It only tells you that your queries are running in parallel. And they are running in parallel because they are more expensive than your cost threshold for parallelism set on an instance level, right? This is the only interpretation of CXPacket. And we will see that CXPacket, and you can see it here already, have an overhead. And the overhead, you can see it here on the right-hand side. This is why SQL Server or the user have to wait longer when the query is running in parallel. Parallelism has an overhead. Nevertheless, CXPacket is nothing you need to worry about, because again, it will only tell you that your queries are running in parallel because they are more expensive than your cost threshold for parallelism. When your cost threshold for parallelism is very high, 50 or whatever, this is already this will already tell you that most of your queries are running in parallel because they are more expensive than 50. That means when you have something like this in an OLTP system, it is very likely that you have to review your index strategy, because in an OLTP system, it shouldn't be the case that a query is more costly than 50, right? So let's go down, and I will show you the following. I will skip this one. I skip. So actionable CXPacket. So let me do the following. I will execute this query here. I create a heap and just select the data from sales order detail into the test table, right? So now I update a record, but I leave the transaction open. This will run forever. So the update is not running forever, but the log which is related to the update will not be released until I either commit the transaction or I roll back the transaction. So when I now reset the await statistics and execute this query in another session, it is blocked because the select will always acquire a shared log. On the other end, I have an exclusive log for the update. So this is a blocking situation. We have two logs which are not compatible with each other. So, and this will take forever. So the problem is the following. When I execute this query, for example, we can see nothing because the session ID is not correct. Do this again. So we can see that this is a query which is currently running, and we can see that this is wrong. This is the 53. Sorry, 53. If this is not working, I will go to the next query. Yeah, this is only working when when the other query is done already. But I should see something like CXPacket somewhere. But for sure, I can also use the wait stats here on a session level, which is 66, and let's do it. So we can see this is the current session, and we can see that we have a log. Yeah, and for the other session, if we close this one, so let me commit this open transaction here. When I now execute the query again, we can see again we are running into logs, yeah, and blocks. So from a DMO's wait stat perspective, when I have something like this, we have wait time which is related to the schema log, because the schema log, this was a log which was not compatible with the update log. And that is the reason why we can see a high number of shared log. I wonder why I cannot see the CXPacket. For some reason, I cannot see the packet here, CXPacket here. Normally, I should CXPacket. Don't ask me why. Maybe the configuration is not the same anymore. But normally, when you see a high number of CXPacket, let's consider that we have a high number of CXPacket here and a high number of log type related wait time. This is an indication that your query is running in parallel because one thread is blocked by a not compatible lock. And that is something which we can call actionable CXPacket. So the reason is not, you do not need to worry about CXPacket, but you have to worry about your block, which is, in this case, a shared lock, which was not compatible with the exclusive lock, right? So that is the reason why you should worry about CXPacket. And for some reasons, again, yeah, sorry for this, but we cannot see a high number of wait time here. Don't ask me why. Normally we should see this, but for some reasons, maybe the configuration is not the same. Okay, last one I want to cover is, I want to go to something which is called thread pool starvation. Let me search for it. Starvation. Yeah, thread pool starvation. So there is a number of worker threads, maximum worker count, yeah, which is available in every system, which is determined by the architecture, which is 32 or 64-bit, by the memory, and I guess also by CPU. So in my system, we have maximum worker count of 576. That means SQL Server cannot execute more threads in parallel than 576. So in order to simulate a so-called thread pool starvation, I set the maximum worker thread to 128, right? Just to avoid that I have to run more than 600 threads at the same time. The maximum number of worker threads is, okay, I think I'm still in a transaction. It's a little bit strange. The maximum worker thread, why it is not changing. Reconfigure. I don't know. That's a little bit strange. I was thinking that I can change the maximum number of worker threads, which normally works, but for some reasons it doesn't work. But I think the example will still work. So we have a cost threshold for parallelism, which is set to 50, and a maximum degree of parallelism, which is set to 8. So when I execute this plan here, or this query, we can see, I do not even need to execute, but this is a serial plan. When I now reset my weight statistics and I run this query with a MAXDOP of 1 in a CMD with O stress to simulate, I would say, concurrent workloads. So that means we are running the query 100 at 100 threads at the same time, but with 2 repetitions. So let me, sorry. As administrator. Come on, here we go. So it is now executing in the background, and what I can do is I can get all the details which are related to the current workload. So, and I will execute another query before the other statement is done in another window. So the interesting part is that currently this is the scheduler, and the scheduler will tell me that the current work queue count is 0. That means all the 100 threads, all the 100 queries which are running in parallel in the background can be handled by the number of worker threads which are available. In my case, it is either 128 or 576. I do not know why I'm not able to change the configuration. Don't ask me. But this means SQL Server can handle the entire number of requests. And once this is done, we should see that all the requests, which are currently in the pipeline. The good thing is, and this is interesting, we will see this. Currently, I limit the number of DOPs, of CPUs to 1. So in the query, we can see the number of requested DOP. And because we are running the query in a serial way, all the request DOP for every request is 1. Okay, so this is something which makes absolutely sense. So DMO's waiting task will tell me I do not have something like thread pool, and I do not have anything which is related to CXPacket. But I guess the workload is already executed. That is the reason why I cannot see anything in DMO's waiting task anymore. But I should see something like thread pool and CXPacket in wait stats. Okay, we can see from a former example, yeah, some thread pools. But again, I will reset the query. And now when I execute the same query again, we should see something interesting. Yeah. It is not running in Perl. I don't know what is going on. I don't know. For some reasons, it is not working. I think some of the configuration is overwritten, which makes the examples not working anymore. But okay, then I need to tell you what you should see because there's only 1 minute left. The problem is the following. When you execute a query in parallel now, let's say with the maximum degree of parallelism of 8, and the cost threshold for parallelism is set to something like 5, and the estimated number, the estimated cost is bigger than 5, then your query will execute in parallel. Fine. So that means the query has the potential to get more and more threads with a maximum of 8. When you now execute the same query, which can run in parallel with the same number of threads, which is 100, that means we are not running 100 times the same query with just one thread. Instead, we are running the same workload with 100 times with 8 threads. That means in the end, we will end up with 800 threads. And 800 threads is more than my maximum worker count of 576. And that is the reason why we should see something like a so-called thread pool starvation in combination with CXPacket. That means when you can see a high number of CXPacket in your wait stats, in a combination with thread pool, so this is the name of the wait type, then it is very likely that you are running into a CPU problem because the task, which is a request, is currently looking for an idle thread within the scheduler. That means the query cannot even start to be executed because it has to wait for an idle thread. And that is called thread pool starvation. So again, when you have a high number of CXPacket in your wait stat, that is normally nothing you should worry about it. It's just an indication that your queries are more expensive than your cost ratio for parallelism. But when you can see CXPacket in a combination with a high number of logs or with something which is called thread pool, then you are in trouble, and then you need to worry about queries which are running in parallel by maybe reduce the number of concurrent queries, or think about the right index strategy to make the query execution cheaper to avoid that queries are running in parallel, so that you do not need to allocate more and more threads for the same query, which leads into a thread pool starvation otherwise. That's it. So sorry that I think the last example was not working. I do not know why. Yeah, so I need to figure out maybe some of the settings I overwritten and I didn't reset. Yeah, then nothing.
I know why. It's because you ran a demo, and then those things happen when you do demos.
That's always the case. Yeah, it's not very easy to demonstrate here. Yeah, so everything has to work because otherwise, yeah, you can see queries are not running in parallel anymore. But at least I hope that you get an idea about the impact of parallelism, and you have seen that. In an OLTP system, queries sometimes are even running slower when you allow a SQL Server to execute your query in parallel. Yeah?
We had this. I worked in a telecom company where they had. I don't know, maybe 10 application servers, and it's very busy because I mean telecommunication, you earn fractions of a cent per call basically. So you need millions of ongoing calls all the time. And they were all writing to a database in SQL Server, and it was using service broker. So you got some extra threads for the service broker queues, and so on. And we didn't really need a big SQL Server. It could handle the load because it was all, very few key lookups and writing one row at a time, small transactions, really fast. But you had so many. Both we needed to increase the number of possible connections, so the connection pool in SQL Server, and the number of worker threads had to be, increased. I think we ran the system on a 4-core server, which was, I mean, big enough, but then you get a very low number for max workers count, and you get also the number of connections. So both of these had to be set to a higher number, which is something we realized when we moved from an on-premise database. It was a physical server, and it was really, it had much more capacity than we needed. I think it had something like 24 cores. So then the max worker threads was pretty good. But then we moved it to an Azure virtual machine with only 4 cores, and nothing worked. So that almost stopped us from being able to migrate until we realized that this is what we ran into.
Yeah, I had one customer. I know we are running out of time, but maybe 1 minute on that. So I had one customer who added a lot of databases in the availability group, right, for high availability. And the problem is, the more databases you have in one availability group, the more threads are already allocated per definition. So even if there is you do not exchange data between the primary and the secondary, even if the database is only there, right, without doing nothing, you already allocate worker threads. And the problem was that the customer was complaining about thread pool starvation, and this was not because of expensive queries. Instead, they had already so many databases in the availability group that the available number of worker threads was less than 50. That means all queries, all user queries, which are now executed by the user, all of them were waiting for an idle thread because there were only 50 threads available. And this was really hard to detect, right? So because you can see a high number of thread pool in your wait stats, but you cannot see the root cause for it.
Yeah, exactly. Yeah, and I think in our case, we had both service broker and we did mirroring. So mirroring takes up, I think, 2 threads per database itself. And then service broker, something like 2 threads per queue. And we had a few of them. So, I mean, it was a very easy fix to just increase it because they were idle threads. Most of the time they didn't. Well, of course, the mirroring was not idle, but for the service broker stuff, they were not busy. So we didn't have a CPU contention basically.
Yeah, true.
So it's but these are kind of edge cases, but you might run into them and especially. Definitely. If it's all TP, you have many transactions ongoing, so you need a couple of threads to run them. So.
Yeah, that's true.
Cool. Torsten, I am going into PI planning.
Yeah, great. That's great. Yeah, let's have a chat later on this.
Yeah. So I am, thank you so much for taking the time to present to us. I am going to stop the recording and for everyone, have a nice evening, have a nice weekend, and we will see each other next week when Jean-Pierre Vogt is going to talk about how to migrate to Azure SQL database using Polybase technology or the Polybase functionality. So I think that's going to be an interesting one. We have some general comments in the chat. Thank you for a great session and have a great weekend. So
Yeah.
I'm signing out. See you. Well, you, Torsten, I will see you every day almost. But for the rest of you, see you in a week.
Okay. Bye-bye.
Bye.